this video we're going to look at another type of graph that's used for grouped continuous data. Just like the cumulative frequency graph and the box plots could be. This one is called the histogram. You did meet this at GCSE, but in a slightly simplified way to how we're going to look at it now. Now, a histogram is very useful for giving a picture of the distribution of the data. By the distribution, we kind of mean the shape of the data. It helps you see the rough location of it. So where is it centered around? What does it go down to? What does it go up to? It also helps you to see the shape of it. With shape, we talk about an idea called skew, which you don't need to know about in detail for this course, but it talks about skew means, is there more of the data at the upper end, or is there more of the data at the lower end, or is it fairly symmetrical with more in the middle and less to either side? And then finally, the other thing that it helps us to see is how spread out the data is, which is linked to this idea of the shape of the data as well. So histograms are exceptionally useful graphs. They are calculated or worked out, we work out how to do it by a simple idea, and that is that the area of each bar is proportional to the frequency that's associated with that bar. Now at GCSE you learn that the area of the bar is the frequency, as in it's equal to the frequency. But at A level, we introduce the idea of a scale factor here, and that's why we use the proportionality symbol. So what we say is that the area of a bar is equal to some scale factor times the frequency. And you'll remember at GCSE replacing this proportionality symbol with equals k times. So that's not a new idea to you, but it is in the context of histograms. Now in the example that's coming up, I'll talk to you about what this scale factor really means, but all we're talking about is sometimes we might have huge numbers here, and by applying a scale factor to the frequency, we can make them smaller so that the graph's easier to draw. Or the other way around, we might have really small numbers and we might want to apply a scale factor to make them larger so that it's easier to analyse the data and it's easier to see the shape of it. So this idea of a scale factor is very useful to us. And the reason a histogram is so good is because you might have bars with different widths, and by making sure that it's the area of the bar that tells you about the frequency rather than just the height, as with a bar chart, it means that each bar looks right. So a bar doesn't look too big compared to another one, depending on what frequency it's representing. So let's have a look at example 5. Now, in example 5, we are told a random sample of 200 students, n is 200, was asked how long it took them to complete their homework on the previous night. So all the data was recorded in a table like this. So 55 students took between 25 and 30 minutes. Time is in minutes, whereas 6 students took between 50 and 80 minutes. And we're asked to draw a histogram to represent this data. So, first of all, we've got to think about this idea that the area of the bar is equal to k times the frequency. And if you're asked to draw a histogram, the first thing and the easiest thing to try is to say, well, let's just make k 1, which means that the area of the bar is the frequency. So what I'm going to do here then is make a note that that means that this frequency here, that is the area. And we're going to write down what the class width is, because don't forget, these bars are just rectangles. So if the area is the area of a rectangle, we need to know the width and the height of the rectangle. So let's write down the name of this column as well. This is called the frequency density, and that's essentially the height of the bar. So this bar here goes from 25 to 30 horizontally, so it's a class width of 5. This one is also a class width of 5, as is this one. This one, however, is a class width of 10, and this one is a class width of 30. So we're going to work out our frequency densities. We need to do, this is the height of a rectangle, this is its width, this is its area, so we're going to do 55 divided by 5, which is 11. So let's just make a little note there so you can make sure you're following what's going on. This one we would do 39 divided by 5. 39 divided by 5 is 7.8. And we carry on, so 68 divided by 5. 13.6. And then 32 divided by 10. And 6 divided by 30, 6/30 is a fifth, so that's 0.2. So we know how wide to draw our bars, we know how high to draw our bars. So prepared earlier, we have our scale here, our axes, and you'll note that I've gone from 0 up to 14 simply because my highest frequency density is 13.6, so no bar is going to be higher than that. And then horizontally, I'm starting at 25. You may have seen in the past people do some kind of squiggly line there before they start. It's not necessary, don't worry about it. We can tell from the scale exactly what's going on. So let's draw our bars. From 25 to 30, so from there to there, we need to draw a bar with a height of 11. Then from 30 to 35, the height is 7.8. From 35 to 40, the height is 13.6. From 40 to 50, the height is 3.2. And then from 50 to 80, the height is 0.2. So we've got a really tiny one at the end here, like that. There we go. Now, I want to point something out to you that's not in the textbook. And I want to talk about this idea of the scale factor here, where the area is k times the frequency. Let's imagine that for some reason we decided that this graph was too big and we wanted to make it a bit smaller. Don't really know why, but you know, there are some times where you might, but using the data we've got, let's work with it. What I'm going to do is now say for a second graph, which I'm going to draw over here, that the area is half the frequency. So I've just made up a scale factor. I've made up a value of k. So let's work out the new area. It's going to be half of this. So we've got 27.5, and then that one's going to be 17 point, no it's not, that one's going to be 19.5. My mental arithmetic is not working today. I'm glad I checked it. The next one's going to be 34, the next one's going to be 16, and the next one's going to be 3. So we've got our new areas, which are half the frequencies. Class widths remain the same, because that doesn't change. This still goes from 25 to 30, this still goes from 30 to 35. But then the frequency density is going to change because the frequency density is the height. So we're going to go area divided by class width. So we're going to go 27.5 divided by 5. Then we're going to go 19.5 divided by 5. 34 divided by 5. 16 divided by 10. And 3 divided by 30. Now, notice something for me here. This is half of this, and this is half of this, and this is half of this. So this scale factor that we applied, because we've kept our class widths the same, the scale factor has been applied to the frequency densities, which means we're going to end up with a graph that's with each bar the same width as the other one, but the height is going to be half of these heights. So imagine taking this graph and just squashing it down by a scale factor of half, or multiplying it by a half. And that's what's going to happen here. So from 25 to 30, we only need to go up to 5.5. So that's going to go to there. Next one, 3.9. Next one, 6.8. Next one, width of 10 going up to 1.6. And the next one, really, really small. I wonder whether I can draw it accurately. Let's try. Really small, going all the way across to there, to 80. So notice it looks almost identical. It's just that these bars are half the height of these. And that's all this scale factor of k does. It just changes the height, all of them in the same proportion. And sometimes that's useful for the way you see a graph. It's useful just for the analysis and the presentation of it. If you're asked just to draw a histogram, take k to be 1. If your numbers come out ridiculously big, you can choose k to be a different value. But it's worth pointing out at this stage as well, with this one here, if I were to draw it, but with a different scale on this axis, so if I said that every 2 squares is worth 1, so 1, 2, 3, 4, it would look identical to that. It's just that these numbers would say 1 through to 7. It would look exactly the same, and that would be my half times frequency. So that idea of the scale factor is only as relevant as the scale you then draw it on. Now, in part B, you are asked to find or to estimate the number of students that took between 36 and 45 minutes to complete their homework. Note the use of the word estimate again, or estimate, simply because we don't know the exact values of each of these times. So, from 36 to 45, let's show where this is on our graph. 36 is about here. 45 is there. We want to find how many students are represented by that area that I have shaded. So let's work out that area. We need to do it in 2 separate sections. We'll take this rectangle here. First of all, it has a width of 4 because it goes from 40 to 36. So that's 4 times by the height of 13.6. And then this, we're going to add to that the area of this rectangle, which goes from 40 to 45. So that's a width of 5, multiplied by its height of, what was it again, 3.2. So let's work that out. We've got 4 times 13.6, add 5 times 3.2. So that's an estimate of 70.4 students. Let's put an approximately equal to. So we could round it down and say there's around 70, 71, round it down or up, so there's around 70 or 71 students. But because it's an estimate, just like when we talk about the estimate of a mean, we'll just give it exactly as it comes out on the calculator, 70.4. Now, let's have a look at example 6. Oh, no, it's worth pointing out there what would happen if I did it on this scaled graph. I would have exactly the same thing going on. I would work out the area of each bar, but I would then have to apply the fact that the area in this case was half the frequency. So I would shade the bars again from 36 to 45, that one and that one. This one would be 4 times by, where were we? 6.8. This one would be 5 times by 1.6. This is going to come out half of 70.4, you'll see, and if you're astute, you'll have guessed that already. So that's coming out as 35.2. But on this graph, when I did this one, the area was half the frequency. So that 35.2 is half the frequency, which means that the frequency is 35.2 times 2, so 70.4. So we still got exactly the same answer, but we just had to apply this scale factor in reverse to find out the frequency from the area. Now, let's have a look at example 6. In example 6, we have a random sample taken of the daily mean temperatures in Herne in 2015. We don't know how many of these values are taken. We're just told it's a random sample. And this is in the large data set. We're told that a histogram was drawn and a group frequency table was drawn as well. Now, what would this table look like? Let's think about this for a second. We've got the daily mean temperature. So we would have a column for temperature. And it would go from something to something, something to something else. Don't know what these numbers are. And then this would be the frequency. Now, what does that frequency represent in this context? It daily mean temperature. So on a certain day, a temperature is measured. Whichever group it goes into, they mark it in here and they write how many days those temperatures occurred on and how many days those temperatures occurred on. So the frequency here represents the number of days. And it's important to do that little exercise so that you really understand what these words are talking about before you plough into the question. Now, part A asks us to give a reason to support the use of a histogram. Why would the histogram be used for this data? Well, that's because the data was grouped, we're told that in the question, and the data is continuous because it's temperature, and temperature is continuous. So grouped continuous data is perfect for a histogram. Next one, write down the underlying feature associated with each of the bars in a histogram. Well, this is the fact that we talked about on the last page, which is that for each bar, the area is proportional to the frequency. And we can write that like this as well. Area is K times the frequency. That's the underlying feature associated with the bars on a histogram. Now we get on to something interesting. So we are told in part C that the bar that represents the temperature from 16 to 18, that rectangle is 3.2 centimetres high and 2 centimetres wide, and the frequency for this class is 8. And we're asked to show that one day is 0.8 centimetres squared. Now, I'm not going to worry about what we're asked to show for a second. What I'm going to do is think about what this bar looks like. So we have, I'm not going to draw it accurately, but I'm going to draw it and write some things on that are useful. So we have a bar going from 16, 17, 18. 16 to 18. And we are told that this bar is 2 centimetres wide. There. We are also told that it's 3.2 centimetres high. So let's, I don't need to do it accurately as long as I write on what's going on. So something like that, something like that. Its height is 3.2 centimetres. Now we are told that the frequency of this bar is 8. But what's its area? That's what we need to know, because we know that the area is K times the frequency. So let's work with this a second. The area of the bar is 3.2 times 2, so 6.4 centimetres squared. Now let's write down this underlying feature associated with the bars. The area is proportional to the frequency. So the area of 6.4 is equal to K times the frequency of 8 for that bar. Now that means we could work out the scale factor for this whole histogram now, because the scale factor is going to be 6.4 divided by 8, and that's 0.8. Now that's interesting because that is something that we were asked to show. We were asked to show that one day is 0.8 centimetres squared. So why does this show it? Well, let's think about that for a second. Let's go back to our statement of proportionality for this histogram. The area is K, which is 0.8, times the frequency. Now we're asked to show that one day is 0.8 centimetres squared. Well, one day, remember the number of days, it's the frequency. So one day has an area of 0.8. One day is represented by 0.8 centimetres squared. That's what we were asked to show. So all we've done is we've worked out the scale factor for this histogram, and we've said, well, therefore one day, plug it into the formula. This here was our proportionality statement for this histogram. Plug in one day and we get the area for that one day. If they were asked to show us, if we were asked to show what area 2 days was represented by, we would just make F2. Or 10 days, we would make F10. So now let's look at part D. We're told that the total area under this histogram was 48 centimetres squared. Find the total number of days in the sample. So what's the total frequency it's asking us, given we know the total area? We are going to come back to this exact same formula again, and that's that the area is K, which in this case we've worked out is 0.8, times the frequency. So if we know that the total area is 48, we are going to find the frequency by doing 48 divided by 0.8. So that's going to be 48 divided by 8 is 6, so that's going to be 60 days. So this sample was taken for 60 days, or n is 60. That takes us to the end of this section. So you now know enough to have a go at exercise 3D.